Imagine if potential energy worked like this. You are holding a ball high above the ground. It has potential energy, right? Let go, and that potential energy converts into kinetic energy as it speeds towards the Earth. Simple enough. But what happens when you are not just falling towards Earth, but you are in space, perhaps caught between the pull of Earth and the Moon, or even a distant planet? How does that potential energy calculation actually shift? That is what we are demystifying today. Let us start with basics. On Earth, gravitational potential energy is often taught as mh mass times gravity times height. The higher you are, the more potential energy you have because Earth's gravity wants to pull you down. This makes intuitive sense. A rock on a cliff has more potential to do work like smash something than a rock on the ground. The key is to think of gravity not just as a downward pull, but as a well in the fabric of space-time. Earth creates a deep gravitational well. To leave Earth, you need to climb out of this well. The higher you go, the further you get from the bottom of the well, the more energy you need to expend, and the more gravitational potential energy you gain relative to Earth. It sounds counterintuitive, but in a gravitational well, moving away from the central body actually increases your gravitational potential energy. Think of it like pushing a ball up a hill. The ball gains potential energy relative to the valley. So, as a spacecraft ascends, it is gaining potential energy with respect to Earth. The maximum amount of potential energy you can gain relative to a body is when you have completely escaped its gravitational pull. You have reached infinity relative to it. To do this, you need to reach escape velocity. This is not a height, but a speed you need to hit to keep moving away without falling back down, essentially having enough kinetic energy to overcome the entire gravitational well. It starts with Earth's dominance. Okay, so you have launched from Earth. Initially, Earth's gravity is by far the dominant force. Your potential energy is entirely dictated by your distance from our home planet. You are constantly working against that pull, converting chemical energy from your fuel into kinetic energy to gain altitude and, yes, that crucial gravitational potential energy. As you journey further out, perhaps towards the Moon or Mars, Earth's gravitational influence diminishes, but it never truly disappears. You are still within its general pull, but now other celestial bodies start to exert their own, albeit weaker, gravitational forces on your spacecraft. This is where things get really interesting, and the simple mg formula becomes inadequate. Now imagine you are heading for the Moon. Just like Earth, the Moon also has its own gravitational well, though it is much shallower. As your spacecraft gets closer to the Moon, it starts to feel a stronger pull towards our natural satellite. You are transitioning from being primarily influenced by Earth's gravity to being increasingly influenced by the Moon's. This brings us to the concept of spheres of influence. Each celestial body has a region around it where its gravity is the primary gravitational force on any object. For Earth, it is a huge bubble. For the Moon, it is smaller. As your spacecraft crosses the boundary of Earth's sphere of influence and enters the Moon's, the center of your potential energy calculation effectively shifts. And here is the cool part. There is not a sudden, sharp line. It is a gradual handoff. You are essentially in a gravitational tug-of-war. For a long time, Earth is winning. Then, as you get closer to the Moon's pull begins to overcome Earth's diminishing distant pull. It is like switching which hill you are rolling down, or more accurately, which valley you are approaching. Does the potential energy get translated somehow? Yes, but not in a simple transfer from one body to another. It is more about how we define the reference frame for that potential energy. When you are far from Earth but close to the Moon, your potential energy relative to the Moon becomes the dominant consideration for local dynamics, even if you still possess a vast amount of potential energy relative to Earth as a whole. I will show you how this works using a simple analogy. Imagine space as a giant, stretched rubber sheet. Heavy objects like planets create dips or wells in this sheet. Earth makes a deep well, the Moon a shallower one. When you launch a spacecraft, it is like rolling a marble across this sheet. It starts by climbing out of Earth's well. Now imagine the marble has gained enough momentum to clear most of Earth's deep well. But then, it starts to approach the moon's shallower well. The marble naturally begins to fall into the moon's dip. In this phase, it is gaining speed, kinetic energy, as it loses potential energy relative to the moon's well. The critical thing to remember is that within the entire Earth-Moon spacecraft system, total energy is conserved. It is just continuously transforming between kinetic and potential energy. You do not lose energy, it just gets reallocated or redefined based on the dominant gravitational influence, and your velocity changes accordingly. What happens next? The gravity assist. This principle of energy transformation is precisely what enables incredible maneuvers like a gravity assist or slingshot. A spacecraft uses a planet's gravitational field to change its speed and direction, essentially stealing a tiny bit of momentum from the massive planet. This is a game changer for interplanetary travel, saving tons of fuel. The spacecraft approaches a planet, falling into its gravitational well, converting potential energy into kinetic energy and speeding up. As it swings around and leaves the well, it uses that acquired speed to gain potential energy relative to the sun, essentially getting a kick that sends it off in a new direction and at a higher velocity relative to the sun. The planet barely notices. Beyond slingshots, engineers use something called a Hohmann transfer orbit for efficient interplanetary travel. This is an elliptical path that essentially lets the spacecraft coast between planetary orbits. You use a burst of fuel to leave one orbit, coast along the ellipse, and then another burst to enter the target orbit. It is all about minimizing energy expenditure. The key to a Hohmann transfer is that it uses the least amount of energy to get from one circular orbit to another. It leverages the gravitational potential energy differences between the two orbits. You effectively increase your potential energy relative to the sun to climb to a higher orbit and decrease it to fall to a lower one. As you fall towards another body like the moon, you are converting gravitational potential energy relative to that body into kinetic energy. Your speed increases dramatically. This is why landing is often the hardest part. You have to bleed off all the gained kinetic energy to safely touch down, usually through retrothrusters or atmospheric braking. So, the potential energy is not translated in a single, distinct chunk from Earth's field to the moon's. Instead, your potential energy is always defined relative to whatever gravitational field you are currently primarily interacting with. It is a continuous function across the entire gravitational landscape, not a discrete handoff. In reality, a spacecraft is simultaneously influenced by the gravity of Earth, the Moon, the Sun, and even other planets. Calculating its exact trajectory and energy state is part of the incredibly complex n-body problem in physics. But for practical purposes, we simplify it by considering the dominant gravitational field at any given time. This leads us to fascinating regions known as Lagrange points. These are specific locations in space where the gravitational forces of two large bodies, like Earth and the Sun, balance each other out. A small object, like a spacecraft, can essentially park there with minimal effort, maintaining its position relative to the two larger bodies. There are 5 Lagrange points in any two-body system. Some are stable, meaning a spacecraft will tend to return to them even if nudged. Others are unstable, requiring active station-keeping. They are like small hills and valleys in the overall gravitational landscape, offering unique opportunities for space missions, such as telescopes or fuel depots. What is fascinating? To Mars and beyond. Consider a journey to Mars. You are not just escaping Earth, you are also entering the Sun's vast gravitational domain and eventually Mars. Each step involves careful calculation of kinetic and potential energy relative to these different, overlapping fields. It is a dance of celestial mechanics orchestrated by clever use of gravity. The precision required for these calculations is mind-boggling. Even a tiny error in initial velocity or trajectory can mean missing your target by millions of miles. That is why interplanetary missions involve constant course corrections, refining the path to ensure the spacecraft lands exactly where it needs to be, years after launch. Think of it as an energy budget. You start with a certain amount of energy from fuel. This energy is used to change your position potential energy and your speed kinetic energy. When you approach another planet, you are spending some of your potential energy relative to that planet to gain speed, which you then have to pay back to slow down. The real insight is that space is not an empty void with isolated gravitational pulls. It is a dynamic, continuously varying gravitational landscape, a complex system of interconnected wells and hills. Your potential energy is always defined within this landscape, and your total energy kinetic potential is conserved as you traverse it. So, when you fall towards the moon instead of Earth, it is not a translation of potential energy from one specific entity to another. It is simply that your position within the larger gravitational field has changed, and the primary downhill direction is shifted. Your local potential energy gradient now points towards the moon. It is an elegant dance. By understanding these gravitational interactions, engineers can plan trajectories that require the least amount of fuel using the free rides offered by gravity wells and slingshots. It is not magic, but a sophisticated application of fundamental physics to achieve incredible feats of exploration. The core idea is that potential energy in space is not a static, isolated concept. It is dynamic, relative, and constantly interacting within a complex, multi-body gravitational system. When you move from Earth's dominant pull to the moon's, you are simply moving through a different part of that cosmic gravitational landscape, and your potential energy is continually being redefined relative to your immediate surroundings, all while total energy of the system remains conserved.